Now I am going to start module 3 of chapter 6. In this module, I shall discuss about solution of two-dimensional wave equation in different coordinate systems. Those are Cartesian coordinate system, plane polar coordinate system and spherical polar coordinate systems. For all the cases, we shall use the method of separation of variables to find the solution. First of all, we shall start the Cartesian case. For derivation, now we are going to the slide show. The wave equation in Cartesian coordinate system is written here. Del 2u del t square equals to c square del 2u del x square plus del 2u del y square. In separation of variables method, we write the solution u as product of capital X, capital Y and tau, and we substitute this solution to equation 1 to obtain the expression which is written in the next line 1 by x del 2x del x square plus 1 by y d2y dy square equals to 1 by c square tau d2 tau dt square. So, first we separate the function of t from the function of x and y, and we assume the separation constant as minus mu square to obtain a periodic solution. Now, the equation for tau becomes d2 tau dt square plus mu square c square tau equals to 0. Now, we separate the function capital X and capital Y in the last line 1 by x d2x dx square plus mu square equals to minus 1 by y d2y dy square is equal to lambda square say, where lambda square is the another separating constant. Thus, the equation for capital X and capital Y becomes d2x dx square plus p square x equals to 0 and d2y dy square plus q square y equals to 0, where p square equals to mu square minus lambda square and q square equals to lambda square, and the constant mu square is equals to p square plus q square. Now, the equations for x, y and tau can be solved easily, and the solutions are capital X equals to C1 cos px plus C2 sin px, and the solution for y is y is equal to C3 cos qy plus C4 sin qy, and the solution for tau is tau equals to C5 cos mu ct plus C6 sin mu ct, where C1, C2, C3, C4, C5, C6 are arbitrary constants, and they are determined from the supplied initial and boundary conditions. Therefore, the solution of two-dimensional wave equation in Cartesian coordinate system becomes u equals to product of capital X, capital Y and tau, which is written in equation number 2. Now, we shall take one example where we need to solve two-dimensional wave equation in Cartesian coordinate system together with some given initial and boundary conditions. For that purpose, we considered a physical problem where we considered the vibration of a membrane which is stretched between the lines x equals to 0, x equals to a, y is equal to 0 and y is equal to b, and the initial condition is given by u at x equals to 0 is equal to 0, u at x equals to a is equal to 0, u at y is equal to 0 is 0 and u at y is equal to b is 0. Now, if we apply the condition u 0 y t equals to 0 in the solution, which is written in equation number 2. So, here if we put x equals to 0, we get C1 equals to 0. So, that is written here, C1 is equal to 0, and if we use the condition u x0 t equals to 0, that means if we put y is equal to 0 in solution 2, this gives C3 equals to 0. So, that is also written here, C3 equals to 0. We have two more initial conditions, which are u at x equals to a equals to 0 and u at y is equal to b is equal to 0. Now, u at x equals to a equals to 0 gives sin p a equals to 0. This implies p a must be equals to m into pi, where m is some integer, or in other words we can say that p is equals to m pi by a, and the initial condition x at y is equal to b is equal to 0 gives sin qb equals to 0, which implies qb must be equals to n into pi, where m is some integer. So, this gives q equals to n pi by b. Therefore, solution u can be written as u is equal to sum over m, sum over n, sin n pi x by a into sin n pi y by b into a mn cos omega n t plus b mn sin omega n t. Here omega depends on both the integer m and n, that is why we have used the suffix mn for omega, and the value of omega is given by mu into c, which is equals to c into square root of p square plus q square. So, that equals to pi c into square root m square by s square plus n square by b square. Now, in this solution, the constants amn and bmn are to be determined, and these constants, values of these constants can be obtained using the other conditions. Now, we consider that the membrane starts from rest with initial position f x y. That means, u is equal to f x y at time t is equal to 0, and the velocity, that means del u del t at time t is equal to 0 is also 0. Now, the condition del u del t equals to 0 gives the value of bmn as 0. Now, if we use the second condition, that means u is equal to f x y at time t is equal to 0. So, using that condition in this solution, we obtain f x y equals to sum over m, sum over n, a mn sin m pi x by a into sin n pi y by b. So, from this expression it is clear that it represents a double sine Fourier series. Now, to obtain the coefficient a mn, we need to multiply both the side of this expression by sin k pi x by a into sin L pi y by b, and then we integrate from 0 to a for x and from 0 to b for y, and using the orthogonality property of sine series, we obtain its value as AB by 4 AKL. So, in this way we can find the values of AMN. Therefore, solution of the given problem or the required solution can be written in the form U is equal to sum over m, sum over n, AMN sin m pi x by a sin n pi y by b into cos omega mn t, where AMN are given by the relation which is written here and the frequency Wmn or omega mn is given by pi c into square root of m square by a square plus n square by b square. Now, we are going to find solution of two-dimensional wave equation in plane polar coordinate system. The wave equation in plane polar coordinate system can be written in the form which is given by equation number 4. Here we are using the same strategy, means we are using the separation of variables method to find the solution. For that purpose, we are writing the solution U as product of capital R, capital theta and tau. Then we substitute this solution to equation 4 to obtain the relation which is written here 1 by r d2r dr square plus 1 by smaller capital R dr plus 1 by r square theta d2 theta d theta square equals to 1 by c square tau d2 tau dt square. So, first we are separating the function tau from the function of r and theta, and we are to get the periodic solution, we are assuming the separation constant as a negative number, which is here is minus mu square. So, the equations becomes, which is written in the last line. Now, we are separating the function of r and theta, and we are assuming the separating constant as lambda square. So, assuming lambda square as a separation constant, we obtain the equations for r and theta, which is written here d2r dr square plus 1 by r dr plus mu square minus lambda square by r square capital R equals to 0. And the theta equation is given by d2 theta d theta square plus lambda square theta equals to 0, and the equation for tau is d2 tau dt square plus mu square c square tau equals to 0. Now, if we see the R equation, this is Bessel equation of order lambda. So, the solution for R can be written as capital R is equal to C1 j lambda mu r plus C2 y lambda mu r, where j lambda and y lambda are Bessel's function of order lambda and of first kind and second kind respectively. And the solution for theta can be written as theta equals to C3 cos lambda theta plus C4 sin lambda theta. Similarly, we can obtain the solution for tau as tau is equal to the linear combination of the sine and cosine function C5 cos mu Ct plus C6 sin mu Ct, where the C1, C2, C3, C4, C5, C6 are arbitrary constants, and the values of these constants can be obtained from supplied initial and boundary conditions. Therefore, the required solution of the two-dimensional wave equation in plane polar coordinate system is U is equal to product of capital R, capital theta and tau, which is written in equation number 5. Now, we are going to discuss an example where we can use the solution of wave equation in plane coordinate polar coordinate system together with some initial and boundary conditions. So, for that purpose we have considered the vibration of a circular membrane whose boundary r equals to a is held fixed. So, u at r equals to a is equal to 0 for t greater equals to 0, and it is also given that u initially the value of u is given by the function f, and the velocity del u del t at time t is equal to 0 is given by the function g. Since the deflection is a single valued periodic function of theta of period 2 pi, so if we look at the solution which is given in equation number 5, since this is periodic in theta, so value of this quantity will remain same if we replace theta by 2 pi plus theta. So, to get the same result, to make it periodic in theta, we should have lambda is equals to some integer m. Therefore, we get the values of lambda as m, where m is some integer. Again, if we look at the solution which is written here, in this solution we know that the Bessel function of second kind, which is denoted by y lambda, is undefined at r equals to 0. Therefore, for this physical problem we need to consider C2 equals to 0. So, here we have taken C2 equals to 0. Now, if we use the boundary condition u at r equals to a is equal to 0, that gives the equation J m mu a equals to 0. Let mu mn, where m is an integer, n is an integer, are the roots of this equation. In this suffix, m indicate the order of the Bessel function and the n represent different solutions. Therefore, the solution can be written in the form u is equal to sum over m, sum over n, j m mu mn r into a mn cos m theta plus b mn sin m theta into cos omega n t plus c mn cos m theta plus d mn sin m theta into sin omega mn t, where omega mn equals to c into mu mn. Now, we need to obtain the values of the constants a mn, b mn, c mn and d mn. To find the values of this constant, we use the given initial condition. If we see the initial condition, it is given that the value of u at time t is equal to 0 is equal to f. So, that condition gives the value of f as sum over m, sum over n into j m mu mn r into a mn cos m theta plus b mn sin m theta, and this condition can be obtained from the general solution putting t is equal to 0. that means from this solution. Now, in this solution, if you apply the initial condition del u del t is equal to g at time t is equal to 0. So, if we apply this condition to this general solution, we obtain another expression g is equal to sum over m, sum over n, omega mn, j m mu mn r into c mn cos m theta plus d mn sin m theta. Now, from these two equations, we have to find the values of amn, bmn, cmn and dmn. And if you notice these two expressions, you can see that these are nothing but the double Bessel and Fourier series. So, to obtain the values of amn, we need to multiply the first equation both sides by j m mu mn r into cos m theta into r, then integrate over 0 to a for r and integrate over 0 to 2 pi for theta. Then using the orthogonality property of Bessel function and the cosine function, we can obtain the expression for amn as it can be noted from the slide. Amn equals to 2 by pi square j dashed m mu mn a whole square and the integration. Here j dashed denote the derivative of j. Similarly, we can obtain the value of bmn, cmn and dmn. The expressions for all the constants can be seen in the slide. Now, we are going to find solution of wave equation in spherical polar coordinate system. The wave equation in spherical polar coordinate system is given by equation 7. Again, we are trying to find solution using separation of variables method. For that, we are writing solution u as product of r, theta and tau. So, if you substitute u, this expression in 7, we obtain the expression which is written in the last line. So, as usual, we first separate the function of t, that means tau first, and we have taken the expression to the right side, and to get the periodic solution, we assume the separation constant as a negative number minus mu square, where mu is a real constant. Again, we are separating the function capital R and theta, and we are assuming the separation constant now as n into n plus 1. Therefore, the equations for capital R, capital theta and tau becomes, which are shown in equation 8a, 8b and 8c. So, if you look at this equation, it is easy to find the solution of this equation. If you start from the tau equation, the solution is combination of sine function and cosine function, and solution can be written here as tau is equal to some constant C5 cos omega t plus C6 sin omega t, where omega is C into mu. Now, if we look the R equation, this is not Bessel equation, but if we give some transformation to the dependent variable capital R, it is possible to reduce the equation to Bessel equation. So, this is the necessary transformation. So, we use this transformation, capital R equals to smaller to the power minus half into capital S. Now, the equation in terms of capital S becomes, which is shown here, and this equation is known to us. This is famous Bessel equation of order n plus half. So, the solution can be written as S is equal to C1 j n plus half mu r plus C2 y n plus half mu r, where j and y are Bessel's function of order n plus half and of first kind and second kind respectively. So, our required variable capital R or the solution for capital R can be written as capital R is equal to smaller to the power minus half into SR. So, the solution can be written in this form, which can be seen in the last equation of this slide. Now, if we look the theta equation, which is given in equation number 8b, this is not in the standard form, but if we do the substitution, cos theta equals to mu dash. In terms of mu dash, the theta equation can be written in the form 1 by mu dash square into d2 theta d mu dash square minus 2 mu dash d theta d mu plus n into n plus 1 theta equals to 0, and this is famous Legendre equation. And we know the solution of Legendre equation are Legendre polynomials. So, the general solution can be written as capital theta is equal to C3 Pn mu dash plus C4 Qn mu dash, where Pn, Qn are Legendre functions of first and second kind respectively. Now, in terms of theta, the solution becomes capital theta is equal to C3 Pn cos theta plus C4 Qn cos theta, and we have already got the solution for tau, which is written in the last line. So, the required solution can be written in the form which is given in equation number 9, which is u is equal to r to the power minus half sum over n. This is linear combination of Bessel function of first kind and second kind multiplied with the function of theta, capital theta plus tau. So, this is our required solution. Thus, in module 3 of chapter 6, we have derived the solution of two-dimensional wave equations. In Cartesian coordinate system, we found the solution is double Fourier series. In plane polar coordinate system, the solution is mixed Fourier and Bessel series. But in case of spherical polar coordinate system, the solution is mixed Bessel and Legendre series. Now, we end this module.